Taekwondo is a Korean martial art mostly known for its emphasis on variety of kicking techniques. Due to its popularity on sparring, it was officially introduced as an Olympic sport in the year 2000. While sparring aspects is the most popular, there is a lot more to Taekwondo, which goes from learning the martial art basic moves to self-defense. Polymers are everywhere, and in Taekwondo we use it every time while learning the martial art. To give some few examples, polymers are in our dobok, that consists of polyester, which makes the clothes light and stretchy, also found in most sport clothes. Belt consists of natural cotton, common in all types of clothes, probably the one you're wearing right now. Shoes has varieties of polymers in them. All the guards and pads that I use when training uses polymers. You may have noticed my assistant here, which is also made from 100% polymer. The head guard and body guard have different outer cover, but have similar inner component. The inner component consists of a polymer foam. There are many types of foam, but in this video we'll look at polyurethane foam. The foam is the most important as it is responsible for absorbing shocks when force is applied from the kick. These guards are crucial in sparring, and it is fundamental as it provides protection, and they are the only areas where fighters can score points with their kicks, to the body or to the head, and punch, which is only allowed to the body. Before we see how polyurethane foam is made, we need to know some basics of polymers, so let's get into it. So, what exactly are polymers? The word polymers comes from Greek, where poly means many and mers means parts. Polymers are also known as macromolecules. Polymers are large molecules made by linking small repeating units called monomers. Here we have a monomer, which links with other monomers to make a large molecule, which is a polymer. We also use the term oligomers, which is Greek for few parts. Oligomers are used to describe short chain molecules such as dimer, trimer, tetramer, and others. There are two types of polymers, natural polymers or synthetic polymers. Natural polymers are found in nature and are classified as DNA, where a sugar phosphate backbone is made of monomers of nucleotides, proteins, which are made of monomers of amino acids, polysaccharide, such as cellulose, which are made of monomers of beta-glucose. Synthetic polymers are man-made polymers and are classified by the mechanisms in which they are made. There are chain growth polymerization, step growth polymerization, and others. For chain growth polymerization, monomers are added one by one at the end of growing polymer chain. Chain growth polymerization occurs in 3 steps. Initiation step, where an initiator reacts with the first monomer to form a reactive species. This is represented by the monomer bonded to initiator shown in red, which is ready to react with other monomers. Propagation step occurs when the growing end of chain reacts with other monomers one by one. And finally, termination step occurs when the chain stops growing and the polymer chain is no longer reactive. In this case, the end of polymer chain is still reactive, so it will have to react with another reactive end of polymer chain or species to quench the reaction. Step growth polymerization occurs when both monomers and growing polymer chains have reactive end groups. Step growth polymerization doesn't usually require an initiator, as monomers are already reactive. During the reaction, any monomers can react with each other in the mixture. This leads to formation of oligomers, shown here. Eventually, as the reaction proceeds, oligomers' reactive end groups will react with other oligomers and are joined to form longer chain molecules. The reactive ends of polymer chain will continue to grow until all the monomers and oligomers are used up. Next, we are going to look at how the growth of polymer chains are analyzed for the 2 polymerization mechanisms. For this, we will consider the molecular weights. To do this, we can calculate the number average molecular weight, Mn, which is the sum of mass of each chain divided by the total number of polymer chains. We also need to calculate weight average molecular weight, MW, which is the sum of mass of each chain squared divided by the sum of mass of each chain. For MW, longer polymer chain counts for more than short ones. Now we can use the molecular weights to calculate dispersity, which is the weight average molecular weight divided by the number average molecular weight. Dispersity tells us the population in the sample. In a population where dispersity is 1, weight average is the same as number average, which suggests length of polymer chains are the same. In a population where dispersity is greater than 1, weight average is greater than number average, which suggests length of polymer chains are different. We can plot a graph to see how the two polymerization molecular weights changes over time. For chain growth polymerization, the growth is linear as it has gradual increase in its molecular weights. Here, monomers are added one by one at the end of growing polymer chain, which are converted to form longer chain molecules. For step growth polymerization, the growth is exponential as both monomers and growing polymer chains have reactive end groups. Only short chain molecules are formed at the start, hence the low increase in molecular weights. As many of the short chain molecules react with each other, longer polymer chains are formed, hence the rapid increase in molecular weights. Now we have covered all the basics of polymers, let's look into how polyurethane foam is made. Polyurethane is a synthetic polymer, and this will undergo step growth polymerization, because both monomers have two reactive end groups, shown in red. The monomers used for these reactions are diisocyanate and 1,2-ethane-diol. These monomers can react with each other to form polyurethane. Let's have a look at its mechanism. For this reaction, we actually require an initiator, so we use DAPCO, which is a very good nucleophile as it has high electron density on nitrogen. Due to it being a tertiary amine, it has +I effect from the alkyl groups. So lone pair on nitrogen is highly reactive. At the start, DAPCO approaches the diol and donates its lone pair of electron to form hydrogen bond. Due to large difference in electronegativity between nitrogen and hydrogen, this makes oxygen more delta negative, hence initiating the reaction. Now, the diol acts as a nucleophile and reacts with diisocyanate. Here, carbon is sandwiched between two electronegative atoms which withdraws electron density from carbon, making carbon more electrophilic. Lone pair on oxygen will attack delta positive carbon at the end. The oxygen forms a new sigma bond to carbon. As carbon can't have 5 bonds, C and pi bond breaks, and electron moves to nitrogen. The nitrogen now has a negative charge, and oxygen has a positive charge. Intramolecular attack happens as nitrogen don't like to have a negative charge, so it gets rid of it by attacking the hydrogen. The electron pair moves from the bond to the positive oxygen. This means the DAPCO no longer interacts with the hydrogen, and its job to initiate the reaction is done. DAPCO is regenerated, so will further catalyze other diol monomers. From this reaction, a dimer has been formed. The end groups are still reactive, so will further react with other monomers and oligomers to eventually form the polymer, which is polyurethane. But we're not done here, as the mixture just forms polyurethane and not a foam yet. So how do we make it into a foam? It's quite simple really. All you got to do is add some water to the liquid mixture. Here is the mechanism. The mechanism is similar to the one we just did for a diol. In this case, we use water instead of the diol to attack the end of oligomers with isocyanate group. Negative nitrogen attacks the hydrogen, and electron pair moves to the positive oxygen. But this time, we have another hydrogen available, so nitrogen can use its lone pair of electron to attack the hydrogen. This leads to OH bond to break, and DAPCO is regenerated. The nitrogen now has a positive charge, and oxygen has a negative charge. The negative charge on oxygen can be used to form a new pi bond between CO, so C and sigma bond breaks and electron moves to positive nitrogen. This leads to formation of primary amine and carbon dioxide. Carbon dioxide gas is produced, which is important and we'll get back to in a moment. New amines can also react with other isocyanate end group the same way water did. This eventually leads to formation of urea linkage instead of urethane linkage. But urea linkage doesn't alter the property of polyurethane that much. So what does? Remember the carbon dioxide gas which we said was important? Well, it is, so here's why. Polymerization reaction begins as a mixture in a liquid, and when CO2 gases are produced, it just bubbles away. But as the reaction progresses over time, the molecular weight increases exponentially, therefore reaction becomes more and more viscous, making the liquid thicker. This is because of increase in intermolecular forces of attractions between molecules due to longer chain molecules being formed. So when more CO2 gases are produced, it becomes trapped as a bubble in the viscous liquid over time. After the reaction is complete, the polymer will eventually solidify and CO2 bubbles stay trapped within the polymer, making it a foam. Polyurethane foam is common in most guards, but it also has many other uses as it's important in making sponge, mats, cushions of car seats, pillows, sofas, and many more. Polymer's properties are determined by the temperature for a specific volume. At a low temperature, polymer is at a glass state where it has properties similar to a glass. Here, polymers are hard and rigid. As temperature increases, it reaches glass transition state, where its properties changes from glass to a rubbery state. Polymer's entropy increases as polymers becomes more disordered. Here, polymers have similar properties to a rubber, as polymer chains have more freedom of movement. This is the property widely found in guards, as its outer cover and inner foam is actually a rubber. That's why you may notice the guards are elastic, soft, and flexible. As the temperature increases further, it reaches melting temperature, where the rubber melts to its liquid state. Here it has properties similar to a liquid and behaves like one. You may have noticed polymers don't have a gas state, as polymers are large molecules which requires large amount of energy to break. Even if we do break it, it's no longer a polymer. Other polymers commonly used in the guards are ethylene vinyl acetate and nitrobutadiene rubber. These can also be used as the outer cover, or its foam can be used as the inner component. EVA and NBR are formed via chain growth polymerization, as they have two monomer units which can repeat and vary in length. These are also known as copolymers. Both guards used in this video actually have their outer cover made of polyurethane, which gives them the smooth surface. For the head guard, the inner component is made of NVR foam, and for bodyguard, the inner component is made of EVA foam. Depending on the brand, you'll find that the guards are manufactured a little differently. So they vary in their use of polyurethane, NBR, EVA, and their foams in the guards. The head guard is soft and light, whereas the bodyguard is stiff and heavy. This is so that when wearing head guard, head doesn't feel heavy and allows freedom for head movement. And when wearing bodyguard, body can handle its weight without hindering the fighter's abilities too much. You may also find that a bodyguard with polyurethane foam is softer than EVA foam. This is just due to difference in density of polymers. Density is considered so polymers' properties are suitable for its use. Polymers having such vast properties are the reason why they are used everywhere. These properties of polymers reduces the chances of any serious injury which may be caused when sparring. However, fighters have to be aware that the guards don't guarantee 100% protection from all the kicks, as some hard kicks can still lead to a knockout even if you're wearing the guard. Due to advancements of technology in the modern world, in 2009, electronic guards was introduced in Olympic Taekwondo. This was done to reduce human error and bias when keeping track of the score. However, electronic guards was not always accurate and only registered certain type of kicks. Fighters became aware of this, which limited their use on variety of kicks, and primary focus became to just score points. This meant we started to lose the dynamics of Taekwondo sport, which made it less entertaining to watch. This goes against the goals of World Taekwondo, which is to ensure Taekwondo gets participation and watched by as many people as possible. So, what do you think the future of Olympic Taekwondo will be? Should the electronics be removed? Or will we find better solution to bring back the dynamics of Taekwondo to the modern era? Do let me know your thoughts in the comment section. Also, if you'd like to know more on the topics covered in this video, check out the description below. Thank you for watching.
Ooh.